Hello students, it's your professor Dr. Mink, and in this lecture we're going to be covering multi-way search trees. This content is covered in chapter 23 in your textbook Java Foundations. In keeping with tradition, we'll cover the chapter scope. For this chapter, we're going to examine 2-3 and 2-4 trees. We will introduce the concept of a B tree, and we'll look at an example of a specialized implementation of B trees. So far in this course, we've looked at trees that had multiple children per node, or general trees, and we also looked at binary search trees where there's a relationship among the elements, but only 2 children per node. A multi-way search tree combines the elements of binary search trees and general trees. Each node may have more than 2 children with a specific relationship among those children. And we're going to look at 2-3 and 2-4 trees next. A 2-3 tree is a data structure in which every internal node, i.e. a non-leaf node, has either 1 data element and 2 children, or 2 data elements and 3 children. If a node contains 1 data element, let's just call it left val, it has 2 subtrees or children, namely left and middle. Whereas if a node contains 2 data elements, left val and right val, it has 3 subtrees, namely left, middle, and right. The main advantage with a 2-3 tree is that it is balanced in nature as opposed to a binary search tree whose height, in worst case, can be O of n. Due to this, the worst case time complexity of operations such as search, insertion, and deletion is O log n, as the height of a 2-3 tree is O log n. And obviously we're going to get further into this, but to summarize, in a 2-3 tree, each node has 2 or 3 children. 2 children if it has 1 data element, 3 children if it has 2 data elements. So a 2-node, a 2- node contains 1 element, a 3- node contains 2 elements. And we're going to see this graphically in a second. A 2- node can have either 2 children or no children. A 3- node has either 3 children or no children. You'll hear a 2-3 tree or 2-3 tree used to reference this. They're both correct. I'm going to start using 2-3 trees instead of 2-3. But anyway, so let's review the relationship among the parent and the children. So in a 2-3 tree, each node has 2 or 3 children. A 2-node or 2- node contains 1 element, and we see 30 as a 2-node. And a 3-node contains 2 elements, 60 and 82. So a 2-node can have either 2 children or no children. It cannot have 1 child. A 3-node can have either 3 children or no children. And you see examples of each in this slide. Here we're going to look at an example of adding 27 to a 2-3 tree. And it may simply add an element to a leaf node. So you see the initial tree, and we're going to insert 27, and it will simply be inserted as a new element in a 2-node becoming a 3-node. 22 is in the initial tree a 2-node, and then 22 and 27 will be a 3-node, which means it can have 3 children. Another example is shown here where inserting an element may split a 3-node and move an element up. So in this example, we can see the structure of the initial tree, and we're going to add 32. So in order to add 32, we're going to take a 2-node 30 and make it a 3-node holding 30 and 35 so they can have 3 children. Those children can be a combination of 2-node and 3-node, but none of them have any children. Remember, a 3-node has 3 children or 0 children. A 2-node has 2 children or 0 children. In this example, adding 55 causes a split of a 3-node whose parent is already a 3-node, and this causes a ripple effect. So look at the initial tree, and we're going to add 57, and 57 would have to go to the left of 60, which is a 3-node, an element, a 3-node. So there's a significant amount of transferring. So the entire tree structure gets changed to accommodate adding 57 and adhering to the rules of a 2-3 tree that can only have 2 nodes with 0 or 2 children, or 3 nodes that have 0 or 3 children. Take a close look. And if that ripple effect propagates all the way to the root, a new 2-node gets created. So the root of this tree was a 3-node that could have 2 children, and now because of the ripple propagation, every node in this tree, including the root, is a 2-node. If we add another element or we delete an element, that obviously could change. Removing an element, and in this example, we're removing 55 from the initial tree on the left, may convert a 3-node into a 2-node. So we're removing 55. The parent, which is a 3-node, remains unchanged, and we simply convert the 3-node, which originally or initially held 51 and 55 with 0 children, which is appropriate, to a 2-node with 0 children. That 2-node holds 1 element and can have 2 or 0 children, and that element then becomes 55. In this example, when removing a 2-node leaf, 22, causes an underflow and requires a rotation, also called a transfer. So we pull an item from the parent and we replace it with an item from the sibling. In this example, the item pulled from the parent is 30, and we replace it with 35 from the child. And this enables us to maintain the rules of engagement for a 2-3 tree. An underflow may also require multiple rotations to maintain the integrity of the tree. So in this example, and we have 3 steps, we're going to remove 30. Okay, so 30 is a 2-node whose parent is a 2-node, which would leave a 2-node 35 with 1 child, and that cannot be the case. So what happens is the 45 is transferred or rotated, if you will, and then again down to it. 45, which is originally our root, becomes a leaf 3-node, and then I'm looking at all the details here. Yes, the 30 gets removed, 35 gets swapped, and 40 then becomes a two-node root with two children that are both two-node. A lot of moving parts. In this example, we're going to remove 55 from a 2-3 tree. 55 is a leaf node, and so that would leave a 3-node with two children, so that won't work. So what happens is the 75 and the 60 get moved down into they get combined to become a 3-node leaf, and 82 is then a 2-node parent to the 3-node leaf 60, 75 and the 2-node leaf 87. Rotations or transfers may not solve everything. Here's an example where every node in this tree is a 2-node, and every node that is a 2-node has two children, except for obviously the leaves at the bottom, which are 2 nodes with no children. So anything removed is going to cause a major problem here. So the entire height of the tree has to get reconfigured. So here's an example. It's the last example for a 2-3 tree where we're removing internal nodes 30 and then 60. So you can see in the upper left-hand corner the initial tree, and 30 is a 2-node parent of a 2-node child and a 3-node child. So removing that is going to require a swap. We're going to, or sort of transfer, rotation, whatever term we're using. 35 will swap with 30, and that will leave us with 30 being replaced with a 35, still a 2-node, with two children that are both 2 nodes. So then remove 60, will be swapped. Sorry, I had to take a close look. I don't have the greatest eyes in the world, probably from working on computers for 40 years. But anyway, so the 60 is part of a 3-node that has 3 children, 3-node, 2-node, 2-node. So rotation will have the 60 removed, the 55 will be swapped up, and then 51 will become a 2-node. So then we're still in an appropriate format with the 3-node 55 containing elements 55 and 82 having 3 2-node children. A lot of moving parts. Pay attention. Take a close look at this on your own and walk through the process. So as you might have guessed, a 2-4 tree is similar to a 2-3 tree with nodes that can contain 3 elements. A 4-node has either 4 children or no children, just like a 2-3. So the same ordering rules apply, and similar cases govern insertions and removal. And we're going to take a look at 2-4 trees, and you'll see it's very similar to 2-3 trees. This slide shows a series of insertions into a 2-4 tree. Now remember, a 2-4 tree, the parent can have 3 elements and it can have 4 children. So first we insert 3, 55, and 14. If it's a 2-4 tree, they're all going to be inserted into the same node, which is a 4-node. 3 elements, 4 children, or 0 children. So then we insert a 25 and the tree reconfigures. 25 will be a 2-node with 2 children, 3-node containing elements 13 and 14 with no children, and a 2-node containing the element 55 and no children. So all the rules are still preserved. Then we insert 40, and 40 will make the 2-node child of 25 a 3-node with no children. So then we insert 22 and 29, and those will make the bottom leaves transition from 3-node to 4-node elements, or 4 nodes. So then we insert 60, and 60 will make the root a 3-node with 3 children, a 4-node, a 3-node, and a 2-node child. And then finally we insert 17, and that will make the root a 4-node with 4 children. 3 and 14 are less than 17. 22 is greater than 17, less than 25. 45 and 55 are greater than 25 and less than 60, and 99 is greater than 60. So there you go. Pretty straightforward, I think, at this point in the lecture. And now, just to close the loop, on 2,4 trees, we'll cover a series of removals from a 2,4 tree. The initial 2,4 tree has a 4-node root, a 3-node child with 0 children, a 3-node child that itself has no children, a 2-node child that has no children, a 3-node child that has no children, and a 2-node child that has no children. Phew, that's a mouthful. So if we remove 3 and 40, okay, we wind up with the same root and 4 2-node children. We remove 17, and the structure changes so that our root is now a 3-node with 3 children. And then we remove 22, and there's the result, 25, and remove 14. Pretty straightforward if you keep in mind the rules of engagement and the structure that must be adhered to given 2-node, 3-node, and 4 nodes. 2,3 and 2,4 trees are example of a larger class of multi-way search trees called B trees. The maximum number of children each node can have is called the order of the B tree. Thus, a 2,3 tree is a B tree of order 3. A 2,4 tree is a B tree of order 4. And using that same logic, here is a B tree of order 6. So a B node in a B tree of order 6 can have 5 elements and 6 children. And that's what we have here. Last topic is some variations on B trees. And before I say anything else, I want to bring your attention to a video I found to be extremely useful. It's an introduction to B trees, and it's on YouTube. I guess he's a TA somewhere, but he's just phenomenal. And I thought I was going to have to create my own video, but I could not do a better job than this individual. So I'd like you to watch that. And it will demystify a lot of the elements of B trees. So a B star tree is a B tree. However, that guarantees that each non-root node is at least 2/3 full. And this avoids the problems of the B tree being half empty. And in a B tree, a B plus tree, each element appears in a leaf, even if it also appears in an internal node. So this improves the sequential access to all the elements of the tree. And once again, I urge you to watch that video so I don't have to spend any more time talking about these variations. It's just a phenomenal video. So now we're going to take a look at a B plus tree of order 6. And let me remind you that in a B plus tree, each element appears in a leaf, even if it also appears in an internal node. So each of these elements, 5, 12, 22, 35, 55, are also featured in the leaf of that, or the children of that root. So there's the 5, there's the 12, there's the 22, there's the 35, and there's the 55. And so the first child would hold all elements that are less than 5. The second child would hold elements of 5 up to less than 12. So it would be greater than or equal to 5, less than 12. Then the third, greater than or equal 12, less than 22, greater than or equal 22, less than 35, greater than or equal 55, 35, less than 55. So I'd be remiss if I didn't bury at least one assignment in this video to keep you on your toes. This is an assignment called the 2-4 tree. I want you to draw a 2-4 tree that results from adding the following elements into an initial empty, i.e. 2-4 tree. And take a picture, whatever, PNGs, JPEG, whatever, and submit that in Canvas. Thanks for watching. Have a great day.